Hello everyone, this is Mr. Couple. This video is for my IB Physics SL Year 1 students, and it is about the kinetic theory of gases. I want to start off by just, you know, taking a step back and just kind of thinking about what we've been doing so far. So we've been trying to model a gas. Like this lesson is going to be the grand finale of everything that we've been working towards. So it's kind of important to take a step back and sort of reflect on what we've done so far. So we started off by thinking about how the microscopic motions of particles, banging into the walls gives rise to this macroscopic property that we call pressure. We've also talked about in the past how the motion of the particles with their kinetic energies gives rise to the temperature. So what we want to do today is, really go into the mathematics and look at the actual physical collisions and model them mathematically using mechanics, with conservation of energy, conservation of momentum. We actually want to go in there and mathematically derive these the relationship between these microscopic properties of the particles moving around and the macroscopic properties of pressure and temperature. So that's the goal with this lesson. It's called the kinetic theory. And so the kinetic theory is when we try to model the microscopic motions of particles, mathematically model them. Now, this is extremely complicated. There's about like in a typical sample of gas in a container like this, there'd be about 10 to the 25th molecules. So that's a lot of molecules, like 100 moles. You're looking at more molecules than you can possibly try to calculate. Like it's insane. Like no computer exists that can do this calculation. So we have to treat things as statistical averages. Like we have to sort of do a few tricks, but it's fine. Like the mathematics can handle it. We'll just realize that we're gonna have to make some assumptions because we're not gonna be able to solve this perfectly. So there are four assumptions that we make with the kinetic theory of gases. These are the assumptions. So the first is that you have a large number of molecules moving in random directions. So you don't just have like a couple of particles, you have, trillions of particles. And that way the pressure is relatively constant, like there's enough collisions with the walls, like bum 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 bum, that it happens quickly enough. There's so many collisions per second that the pressure just ends up being constant. Also, you need a large number so that statistical averages have meanings, since we're going to be using statistical techniques. Number two, the molecules are on average far apart from one another. This allows us to ignore their interparticle potential energies, interparticle forces. We can ignore that because we're just going to say, hey, the only time that the particles interact is when they collide. So they're far enough apart that we can just ignore that whole mess of potential energy and interact and interparticle forces. The third is that the molecules obey the laws of classical mechanics, mainly Newton's laws of motion or Newton's second law that forces the rate of change of momentum. And then the fourth one is that we're going to assume the collisions are perfectly elastic. So anytime two particles collide, it's a perfectly elastic collision, or if a particle collides with the wall, it's a perfectly elastic collision. Now, when we look at the particles in a sample of gas like this, they're all randomly moving around in every which direction. Like you guys have seen that in the simulation. These particles just flying everywhere. There's really, if you imagine you made a graph of how many particles, how many molecules had each speed, you'd end up getting a graph that looks like this. This is called a Maxwell Boltzmann distribution. So the number of molecules against the speed, and you end up getting this distribution. So you'd see like there's a couple of particles, like very few of them, that have low speeds, and then there's very few of them that have high speeds. Most of the particles are in this region here with a lot of speed, like this middle-ish speed, right? All right, so my first question is, what the heck is the meaning of the peak? So what is the meaning of the peak of this curve right here? So what is the meaning of this peak? So this peak would be the highest number of molecules. So we call this the most probable speed. So this is the most probable speed. So the way to think about that is like if you just took a particle at random and like grabbed it. I'm taking my keyboard off right now. If you just took a random particle and grabbed it, most likely it would have this speed. It would have the highest probability of this speed. So we call it the most probable speed. That's not the only speed that you can measure. So there's the most probable. So I'll put that as like a dot. So this is the number one. That's the most probable. There's also the average speed of the particles. And so that I'll put that here. That would be like number two. That's the average speed. You'll notice that the average is shifted a little bit to the right of the peak. And the reason why is because this graph isn't perfectly symmetric. Like if I tried to draw like a perfectly symmetric graph, it'd end up looking like that-ish. I don't think I did a very good job of that. Like that. And then if I came down the same way I went up, it would look, let me try it one more time. If I came down the same way I went up, it looked like that. So you can see that the graph actually has this pretty long tail out here, and that ends up shifting the average over from that most probable speed. And then the last speed that we like to talk about is called the RMS speed, the root mean square speed. The root mean square speed ends up being about here-ish. Let me zoom in. What the heck is it? Okay. So the root mean square speed ends up being here. So what is the root mean square speed? The root mean square speed is just, take the average speed, but just square each individual particle. So instead of taking the first one plus the second one plus the third one and all the way out to the nth particle, you just square each velocity. Now, why would you do this? Well, the reason is because velocity is a vector. So we want to square it out to get rid of negatives. So the velocity is squared to remove negatives, which could result in zero average velocity. So we don't want that to happen, right? You imagine like if you had a particle that was moving this way and another one that was moving this way, the average velocity could end up being zero. Like if these guys both had the same velocity, but they're in opposite directions, the average velocity could be zero. And that's not good because they have to have energy. Like the particles, there's energy in this box. These particles have energy, and we don't want energy to get to be zero. And so there's a trick that physicists will do and where they'll calculate the RMS speed because the RMS speed can never be zero. So it's this little trick that you do where you just square everything and then square root it. And then that way you're kind of like back to where you started from in a sense. And then you're able to just avoid this problem of having zeros. But you're not perfectly back to where you started from. Like, taking the square root of two things that are squared added together, the square root doesn't cancel out like that. Like you can't say that, x squared plus y squared square root of that. You can't say that that's equal to x squared or x plus y. That's not the case. Like those aren't the same thing. So you're not going to have an exactly equivalent situation. It will slightly increase the speed when you do that. Okay, so oh yeah, I was going to show you guys this graph. Let me see if I can find it real quick. Let's see. Online teaching here, week 5. Maxwell Boltzmann distribution. Okay, here we go. So come on, come on. Okay, here. So this is the gas at different temperatures. So I just showed you guys like low temperature, like 100 Kelvin. But if you heat up the gas to 1200 Kelvin or heat it up to 3000 Kelvin, you'll notice that the curve actually distribution changes. So we see that there's a larger there's particles now that are out in the higher velocities because the gas is hotter, so there's going to be faster particles. But there's less probability of finding any one particle at any one speed. It's more like this spread out distribution. So at low speeds, you have this clumped distribution, like a tight distribution. Higher speeds, it gets more spread out. And you'll also notice the 1, 2, and 3, they're very close together. You can notice that as we heat it up, they get more apart from each other, but at low speeds, at low temperatures, they're relatively the same. So what we're going to do in IB physics is we're just going to say, hey, you know what? These three speeds, they're all different, but they're close. Like they're numerically different speeds, right? Like each of these speeds is a different speed, but they're all fairly close to each other. So you know what we're going to do is just to make things easier at the high school level, we're just going to use the symbol C for all of them. We're just going to say they're all the same. I mean, it's technically wrong, so it's not technically correct, but we can just assume that they all mean the same thing and they're just going to use the symbol C for it. And then I'll use that assumption a little bit later. It's going to be wrong, but it's trivially wrong, so we're not going to worry too much about it. It's negligibly wrong. Okay, before we get into actually like thinking about all the particles within like modeling all the collisions, I just want to look at one collision. So let's consider a single particle, and the particle is going to have mass m, and this particle comes flying in and it hits the wall of the container. And so we just want to look at what happens when this particle hits the wall of the container. Well, we know what's going to happen. I'm going to turn off my camera. It's getting in the way. All right, so what we know what's going to happen is the particle is going to exert a force on the wall. And then the wall is going to exert a force back on the particle with Newton's third law. Remember, we said that it's obeying the laws of mechanics. So the particle hits the wall, and then the wall hits back. But realize that that force that the wall hits back with, the wall can't push. The wall can only push perpendicularly. The wall can't push, the wall's not going to push something up or push something down. The wall can only push something back. And what that means is that the vertical velocity, if we draw the vertical component of the velocity of the particle, the vertical component of the velocity is not going to be able to change. And we remember this, that the force is the change in momentum over the change in time. So momentum, the only way that momentum can change is if there's a force. And since there's no force in the vertical direction, the vertical velocity can't change, or the vertical momentum can't change. So the vertical velocity is going to stay constant. So we can say that Vy is constant since Fy is equal to 0. That means that the only thing that's going to change is the horizontal velocity. So the velocity in the x direction. So I'll call that Vx. The Vx is the only thing that can change, because that's the force that's going to change it. So you imagine like the particle's coming in with this velocity, it hits the wall pushes it back, turns the velocity around and points it in the opposite direction. But because the collision was elastic, so since it was elastic, the magnitude of Vx before and after has to stay the same. The speed has to stay the same since it's elastic. So the Vx magnitude here are going to be the same, but they're pointing in opposite directions. So if we want to calculate the change in momentum, so the change in momentum is just delta quantity mv, right? Because momentum is m times v. And so we realize that the change in momentum is simply going to be m of the initial velocity, which was, final velocity. It's final minus initial. So it's the final velocity, which was mvx, minus the initial velocity, which was negative mvx. And we can see that this particle is moving to the left, so it had a negative velocity initially. And then what happens is when you subtract a negative, you end up getting an addition. And so the change in momentum is actually going to be 2m Vx. And so that's the change in momentum that a single particle experiences when it hits the wall of the container. So what we're going to imagine is you've got this particle here, and this particle is just, flying around like jum, 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 all over the place. What we're going to do is we're just going to consider the horizontal motion of the particle. So we're just going to consider the motion of the particle left and right. And so we can just sort of ignore the rest of the motions and just say, hey, you know what? I'm just going to focus on the particle moving left and right. So let's imagine a particle that starts off right here. So the particle starts here and it starts moving in the x direction towards the left-hand wall of the container. So here it goes. So the particle starts to move like this and it reaches the end here and then bonk, it hits the wall and then it bounces back and it bounces back in the opposite direction. We're going to say that the time it takes the particle to do this, to go to here and then back again, we're going to say that that time is delta t. So the time it takes the particle to go to here and then back again, we're just going to call that delta t. So realize that the particle, like this particle that we're thinking about, is going to experience many collisions with many walls. But we're just going to say the time between collisions with this side wall is delta t. Okay, a few things also to notice is that the length of the sides are L. So you have L times L times L to give you the volume. So the volume of this container is L to the third power. And remember that there are N molecules and each molecule has mass M. So N total molecules and each molecule has mass M. Okay, the last thing to notice is, so what's the distance that the particle traveled in delta t? So in the time delta t, the distance the particle traveled was it traveled 1L to the left and then 1L back. So it traveled a total distance of 2L. Okay, let's determine an expression for the time. I should say delta t. Let's determine an expression for the time delta t in terms of L. So we know that distance is equal to velocity multiplied by time. The distance the particle traveled was 2L. The velocity, we were just considering the x velocity, and then the time was delta t. So we can solve for delta t. So we get that the time between collisions is simply 2L divided by v sub x. This, now that we have the time, this actually allows us to determine the force, because the force is the change in momentum over the time. We know what the change in momentum is when it hits the wall. Oh, we did it up here. When it hits the wall, the change in momentum is 2m vx. So I can substitute that into the top, 2m vx. And then the change in time was 2L over vx. So 2L over vx. And then if we look at this, it ends up simplifying because you're dividing the bottom by vx, which means you can actually move that vx up to the top. So if I multiply the top and the bottom by vx, so then what will happen is that the vx down here will cancel out, and then you can see that we end up with f being equal to, and the 2's also cancel out. We end up getting m v subscript x squared divided by L. So that's the force of one molecule. That's the force that one molecule exerts on the sidewall of the container. Okay, before we go any further, I want to talk more about, we just looked at the x direction. So we just looked at one particle that was moving horizontally, but we could also look at the particle's motion in any direction, right? So we could say, all right, the particle has, I'll just pick a particle. So there's a particle and it has, a vy velocity, it has a vx velocity, and I did this wrong. That's the vz. And then it has a vx velocity this way. And so what we'll do is we'll just say, hey, you know what? Because the velocities are all random, like the particles are moving in all these different random directions, then we can just say that all of these velocities are equal to each other. So vx equals vy equals vz. There's no preference for the velocity that these particles move in. So we could just say that they're all equal to each other. And then the second thing we can say is that if you have a particle that's moving in all three directions, then you can write down that its total velocity. So the total velocity of a particle in all three directions is equal to, this is just Pythagorean theorem, vx squared plus vy squared plus vz squared. It's easier to understand this this is why I usually put a line on my z, because sometimes my 2's and my z's look the same. Imagine you had a particle that was moving two-dimensionally like this. So it had an x component this way, and it had a y component this way. Then we would say that v is that. Well, it's very clearly here to see that v is equal to the square root of vx squared plus vy squared. Or Pythagorean theorem says v squared equals vx squared plus vy squared. And so that's what we're doing over here. We're just adding in that extra third dimension, which is not a problem. That's how it works out mathematically. I don't think you guys have really gotten into three-dimensional mathematics yet, but that's how it works. And we also said that Vx was equal to Vy was equal to Vz, that there is no preference for the direction the particles move. So that means that, any given particle is moving as much in all three directions. And then we could also say that that means that the square of them are all equal as well. And then realize that what this means is that each of these are the same. So Vx squared, Vy squared, Vz squared, those are all the same because they're all equal to the same thing. They're all equal to each other. So realize what we actually have here is we have V squared is equal to 3 Vx squared. So if we say that if Vx squared is Vy squared, then that means that this is Vx squared, this is Vx squared. So what we really have here is we have Vx squared plus Vx squared plus Vx squared. Right? And that's just 3 Vx squared. Hopefully that made sense. I'm going to erase this because I think it's too much. And we get this, and then we can solve for Vx. And the reason we want to solve for Vx is because that's what's in our expression up here, is we really want to know what Vx squared is. So we can substitute it up into there. So if we solve for Vx squared, we get that Vx squared is equal to 1/3 of V squared. And then this is where we're going to make our substitution. Instead of saying, V as being one of those three, we're just going to say it's all of them. And so we're not going to distinguish between whether it's the most probable speed, the average speed, or the RMS speed. And we're going to use this as our value of what Vx is. And so you guessed it, we're going to take that and substitute it back into there. And so that's going to tell us the total force. So before we do that, though, we need to realize that we want the total force now. Remember, this is the force from one molecule. So it would be the total force. So it's kind of logical to think that the total force will just be N times the force, that force of one particle. So I'll just put this as like F sub 1. So this is like the force of the first particle. We'll realize that all the particles will exert the same force on the wall. And so we can just substitute now the value that we had of F1, which was m Vx squared over L. So I'm just taking my mvx squared over L and I'm just substituting in there for F1. So we're realizing like, hey, there's n particles, but n particles all times the force of one particle. That'll give us the total force of all those particles, right? So like if one particle hits the wall with 10 newtons, then 5 particles would hit the wall with 50 newtons. It's sort of that idea. Obviously, they don't hit with that much force, but it's just giving it as an example. Okay, so next, the last thing we're going to do is we're going to substitute in that 1/3 c squared is what Vx squared is. So this Vx squared right here, we need to substitute for 1/3 c squared. And then we'll end up with this expression that F is equal to N m c squared divided by 3L. And so that divide by 3 right there just ends up going down there to join the L on the bottom. So this is our expression for the total force of all the particles. We're almost done because we don't notice that force. What we notice is the pressure. Pressure is force divided by area. So all we have to do is take this force expression here, N mc squared over 3L, and then I just need to divide it by the area. And so I'll just put a divide area down there. So that's all I'm doing is I'm just taking the force and just dividing by the area. So now this is the pressure. Something cool happens right here is we get AL. AL is just the volume of the container. That's the volume of the container. So we can just call that capital V. And if you don't see it, I'll show it to you guys up here. So if we have the area of one wall, so we're talking about the area of one wall. So if that's A, then L is this side here. And then you can see that the volume is just the product of those two things together. So also you can think about the volume as L cubed. Well, A is L times L, right? It's length times this length here. And so then you end up seeing, oh, AL is the volume. And then that's it. I'm just going to make that substitution here. So we get pressure is equal to N mc squared divided by 3 times the volume. I'm just putting those little serifs on there so I don't get confused and think that this is a velocity, because there is that potential, that possibility of that happening. Okay, so now this is our pressure. That's the pressure of the gas. And that's the macroscopic pressure, like the human scale, like the large scale pressure, in terms of microscopic quantities, the number of particles, the mass of, or I should say the number of molecules, the mass of the molecule, and then the speed of each molecule. Those are all microscopic properties that are giving rise to this pressure. Let's just double check to make sure that this expression makes sense, right? So if we think about it, like if we have more particles, we would expect there to be more pressure, right? If you have a larger number of particles hitting the walls, you get more pressure. So that checks out, that makes sense. What if the particles were moving faster? So if they hit the walls with a greater velocity, yeah, they'd exert a greater pressure on the wall. We see that as well, the direct relationship there. And then lastly, we know that if we increase the volume of the vessel, the volume of the container, then that's going to decrease the pressure because the particles would have to travel a greater distance, so there'd be less frequent collisions with the walls. And so that makes sense as well. So that's our expression. Okay, so now I'm going to write this down here. So I'm going to write down our pressure. So pressure equals to Nmc squared over 3V. But we also had another equation for pressure. The other equation for pressure is PV equals nRT. That's from the equation of state for an ideal gas. And we can actually notice that we can set these equations equal to each other. So I can take the pressure from here, from the top, and I can actually substitute it into the equation right there. And let's do that, and then cool stuff will happen. let's see. Yep. So here we go. So I'm going to write down N. So right up here. So N mc squared divided by 3V. So that's my pressure, and I'm going to multiply by V is equal to nRT. And then first, right away, we see that the volume cancels out. Okay, next, it turns out that I know this because I've done this before, but this mc squared here is almost kinetic energy, right? Because kinetic energy is 1/2 mv squared. So that's very close to being kinetic energy. So what we're going to do is just move everything to the other side except for the mc squared. So I'm going to write down mc squared is equal to, so let's see, so we had to multiply the 3 to the other side. So I have 3 nRT, and then that's going to be divided by big N. Big N. Okay, cool. And then let's see what else is going to happen here. Oh, the other thing is, well, this isn't quite kinetic energy, but it almost is. I just have to put the 1/2 in front of it. So I'm just going to put a 2 right there. And so now this piece here, this whole side of the equation right there, is simply the kinetic energy. And then we just have to rearrange this side. This looks super disgusting and super gross. So we're going to make a whole bunch of recollections. So first up, the number of moles divided by the number of particles, that's Avogadro's constant. Actually, no, it's not. It's 1 over Avogadro's constant. You know, but there's an easier way of showing this. Okay, watch. So check this out. So N, the total number of particles, is the number of moles multiplied by Avogadro's constant. Right? So we're taking like 5 moles and we're multiplying it by a number that's trillions. The size of it is like a trillion, and then we're going to get like the true number of particles. So if we think about it as little n over big N, so that means that if big N is n NA, then we'll have n over n NA, and so we're going to end up with 1 over NA. Okay, that's not confusing, is it? Also, the other thing to realize, like all of this stuff here, this stuff is all constant stuff. So what we really want to do is rewrite this constant stuff. It turns out, I'll just show you guys what it's equal to. It turns out that it's equal to 3 over 2, and it's this thing called Boltzmann, the Boltzmann constant, which is all that nr, number of moles times the gas constant divided by the number of particles, ends up being Boltzmann's constant. But I want to show you guys a little bit more in detail of how you get there. Okay, so first up, we can see that n over n is equal to 1 over Na. So now if I just stick an r in there, then we have r over Na. And so that's the trick, is that we say that the gas constant divided by Avogadro's number, that's equal to the Boltzmann constant. So this is the Boltzmann oh, Boltzmann's constant. And if you want to know the value of Boltzmann's constant, you can look it up in the data booklet for IB Physics. It's right here. And so basically the way you get the Boltzmann constant is you just take the gas constant, 8.31, and you divide by 6.02 times 10 to the 23rd. And so that makes sense then why that's negative 23rd. Well, it's because we took this number and divided it by 10 to the 23rd. So it became a very small number down there. And so that's Boltzmann's constant. So 1.38 times 10 to the negative 23rd. So I'll just write it down here. So KB is equal to 1.38 times 10 to the negative 23rd. And then the units are, well, I don't remember, joules per Kelvin. Joules per Kelvin. Okay, there we go. But this is the equation. This equation is called the Boltzmann equation. And it says that the macroscopic property that we know of as temperature is proportional to, this is your proportionality coefficient, is proportional to the kinetic energy of the particles. And so that makes a lot of sense, right? If the particles move with a greater kinetic energy, that's because they have a greater temperature. So that's the end of this video. I just wanted to keep it sort of focused on the derivation because there's a lot here. You don't need to know how to do every step of this. You only need to know how to do like in between parts. Like you absolutely know how to calculate the change of momentum when a particle hits a wall. What else? You need to know this stuff down here. You need to know that Boltzmann's constant is R over NA. You need to know this equation. But all these other details in between, you don't really need to know about. And then the last thing is you need to know about the um, assumptions that we made in deriving this model. You will have to be aware of these assumptions. And that's it. So what I'll do next week is I'm going to actually do problems with you guys. Like there's not enough time to do problems today. I just wanted to do the derivation. And so we'll actually solve problems next week. All right, guys, have a great day. Thanks for watching.